Hello everyone. I am going to talk about the interaction of microwave coupled ferrimagnetic sphere with laser. I am a postdoctoral research fellow in the Department of Electrical Engineering under Professor Yale Books. Many groups are working on microwave qubits. Our group's aim is to create a microwave optical interface which is essential for the quantum information processing, as optical photons are a good carrier of quantum information up to long distance due to their long coherence time. Especially the magnetic materials are good candidates to realize hybrid quantum system, as they can be efficiently coupled to both microwave as well as optical wave through their spin waves. And also another advantage of these spin waves are they have in the magnetic material they have long coherence time. So ferrimagnetic yttrium iron garnet are promising among magnetic metals for strong interaction with microwave due to their high spin density, and in addition to that, X-sphere can act as a optical cavity for enhanced light matter interaction. So for coupling both the optical wave as well as the microwave with respect to our ferrimagnetic sphere, so we have coupled the ferrimagnetic sphere resonator with a loop gap resonator which operates at the microwave frequencies, and we couple the optical light into the ferrimagnetic sphere resonator with a single mode fiber. So the outline of my talk is to explore the microwave induced effect on optical properties of X-sphere and to use it as a sensitive detection of sensitive optical detection of magnetic resonance. So in the second part, we have a proposal for quantum measurement using fiber optical loop mirror interferometer with the ferrimagnetic X-sphere. So in the first so we have we have studied the optical transmission of light passing through the ferrimagnetic sphere resonator coupled with the microwave resonator and while it interacts with the microwave. So these red color components are the optical components, and these purple color components are the microwave components. For the optical transmission of light passing through the FSR and loop gap resonator system, we either use an erbium source laser, which is a broadband laser, or we use a tunable laser. And to collect the transmission of light, we either use a optical spectrum analyzer for the broadband source and a photodiode for the tunable laser source. And to interact with the interact the microwave with the FSR LGR system, we either we use a microwave signal generator at low power or high power, and to detect the system resonances of this coupled system, we use a VNA. So we did both the microwave reflectivity measurement as well as the optical transmission measurement. We see that the frequency these FSR modes and LGR modes form a strong coupling between them, and this coupling strength is 16 megahertz. So near this anti-crossing regime, we did the optical transmission measurement with varying the microwave driving frequency, and what we saw that a periodic pattern of transmission peaks in the wavelength range while we drive the microwave frequency closer to the anti-crossing regime. So this periodicity of this wavelength spacing corresponds to 1.8 nanometer, which corresponds to the free space cavity wavelength of 650 micron. So this free space cavity length can be attributed to the spacing between the two optical fiber ends which containing the X-sphere. So to detect further this correlation between this optical measurement and the microwave resonances, we did the lock-in measurement at low power of minus 10 dBm microwave power, and we saw that the VNA, we see a strong coupling between the LGR mode and the EG mode, LGR mode and EG mode. Then in the anti-gravity, and we did the simultaneous measurement of the lock-in measurement of optical transmission intensity. And as we see that wherever the EG resonance is, our optical transmission measurement is peak is all following this magnetic resonances, and where there is the anti-gravity frequency gap, there we see a drop in optical intensity. So this correlates the optical detection of magnetic resonances. To see the what is the mechanism behind this optical detection of magnetic resonances, we measure the lock-in response as a function of modulation frequency, and as we see there is the lock-in signal drops as we increase the modulation frequency. So the drop in lock-in frequency, we fitted with this an expression which is proportional to this factor, and the fitting data, the decay rate corresponds to this matches with this line width of these EG resonances. So this tells that our lock-in response is limited by the ferrimagnetic resonance line width. So this indicates that the optical detection of magnetic resonances have the signature of magnet optical coupling. So now the optical pulses are necessary to detect very fast magnet optical processes like inverse Faraday effect, which can play a role in quantum computing. So for that we have made a fiber loop figure eight fiber loop mirror, fiber loop laser, in which this left loop acts as a, in the left loop the light propagates in one directions, but the right loop acts in the right loop the light can propagate both clockwise and counterclockwise, and this 50-50 coupler can act as a interferometer. So overall this loop, right loop, acts as a nonlinear loop amplifying mirror, and we to detect that whether our laser has the mode locking or not, we measured the RF spectrum and from this photodiode of the optical photodiode collecting the intensity from the optical pulses, as well as we measured the time response of these pulses through the oscilloscope, and the spectral, we measure the optical spectrum, and we see that a frequency comb is shown in the RF spectrum, and we see the evenly spaced the pulses and a broad optical spectrum, so which confirms that we are at the mode locking regime of the laser. And we also carried out the intensity autocorrelation measurement to show a pulse width of 3 picosecond. So now we have made a proposal for the quantum measurement using the figure eight using the fiber optical loop mirror interferometer. So the basic idea of this is to measure the state of the quantum through this fiber optical loop mirror with the interferometer. So when an optical pulse enters through the channel A1, it can be detected in the channel A2 through the two clockwise and the counterclockwise trajectories, and the detection intensity is the interference of these two trajectories. So it turns out that this device works in such a way that these two trajectories will interfere destructively, and the detected signal in the photodiode will be a dark state. But when we associate we integrate an external environment with this fiber loop mirror, and then we can state change the detection signal in the photodiode, and as well as the state of the of this external environment. So this external object can be a ferrimagnetic sphere resonator, which can strongly interact with the optical pulses, and this probability of transmission along this photodiode of channel A2 depends on this expression, where this chi m depends upon the overlap of these two coherent states, alpha plus and alpha minus, where alpha plus is the pulse is the state of this magnetization of the sphere after the clockwise pulse hits the sphere, and the alpha minus is the state of magnetization after the second pulse hits the sphere. So we have kept we basically propose to keep this FSR in the inverse Faraday configuration, where before the pulse hits this coherent states of the state of magnetization remains in the smaller circle of the phase space. This smaller circle means the magnetization angle, the angle between the magnetization vector and the static magnetic field is small. But when we apply a pulse, the clockwise pulse, then this the coherent state can jump to the bigger circle, and then it can evolve unitarily in this circle. And when the counterclockwise pulse hits the second the sphere, then this state can jump to the bigger sphere also. And so depending on this overlap of these two states, we can control this chi m and also the transmission signal. And it is to be noted that while the after the application of the first pulse, or between the so T1 is the time when the first pulse hits the sphere, and the first partial pulse hits the sphere, and the T2 is the time when the second partial pulse hits the sphere. So in between the time, so we are not sure that whether the pulse will hit pulse is in the clockwise trajectory or the clockwise and counterclockwise trajectory. So it is an entangled state, but after the time T2, so we can control the entanglement of this coherent final state. So another point is when, so since this has a precession period of it has a magnetic resonance frequency, and so when our time period is the half of the magnetic precession period, and these two states can completely overlap on each other, and giving chi m is equal to 1. So we can see the photodiode signal as the dark state, which is that means the states becomes completely disentangled. And if it is not this, if we are not matching this condition, then we are in a partially entangled states. So in the summary, we detected the optically detection of magnetic resonance near the anti-crossing region of FSR and EG resonance, FSR and LJ resonance, and we made a proposal to control the entanglement of states using ferrimagnetic sphere and FLM interferometer.
Okay, thank you,
Thanks to our group, and thanks to